Hello everybody, welcome back to my channel VKS Chem Tutorial. In this video, we will discuss an important rule for calculating absorption maximum in organic molecules. Right? After watching this video, you will be learned how to calculate the lambda maximum of conjugated dienes, acyclic conjugated dienes, heteroangular dienes and homoannular dienes. Okay. Woodward and Fieser formulated an empirical rule for calculating the lambda max for these dienes. Before going into the calculation of lambda max, you will have to consider some of the important terms used in this rule, Woodward Fieser rule. Right? For example, dienes exist in two conformations as cis-oid conformation and transoid conformation. Transoid conformation is otherwise called S-trans conformation. Cis-oid conformation is called S-cis conformation. S means single bond connected to two doubly bonded carbon atom, two double bonded carbon atom. Okay, it is S-trans conformation where the double bonds are oriented along the opposite side of carbon-carbon double bond, and it is S-cis conformation or cis-oid conformation in which the double bonds are oriented along the same side of carbon-carbon single bond. See, because of this orientation, the double bond oriented along the same side in cis-oid conformation, there will be some electrostatic interaction between this double bond pi electrons of the double bond because it is oriented, these bonds are oriented along the same side, and hence cis-oid conformation is unfavorable, usually less favorable compared to S-trans conformation or transoid conformation because of the presence of this interaction, electrostatic repulsive interaction, the ground state of cis conformation gets increased, the energy of the ground state gets increased, and hence it will be less stable because of the this higher amount of energy acquired by this interaction, repulsive interaction. That is why the ground state is less stable compared to the ground state of transoid conformation. Okay, and hence cis-oid conformation is less favorable compared to the transoid conformation, and hence muted as usually the dienes, especially cyclic dienes, usually exist in S-trans conformation. But cyclic dienes, these double bonds are trapped inside the cyclic ring or the ring, and hence they are favorable compared to S-cis conformation in acyclic compounds. Okay. See, cyclic dienes may be homoannular diene or heteroangular diene. In homoannular dienes, conjugated double bonds are present in the same ring. Conjugated double bonds are present in the same ring and having S-cis-oid configuration. S-cis-oid configuration. You can see S-cis-oid configuration in this homoannular diene. As I have discussed, S-cis single bond joining two doubly bonded carbon atoms. Okay, and these two are examples of homoannular diene that in these compounds you can see the double bonds are the conjugated double bonds are present in the same ring, and so these two are examples of homoannular diene. As I have discussed, the cis configuration, S-cis configuration causes strain which raises the ground state energy level of the molecule, leaving the high energy excited state relatively unchanged, and hence the homo-LUMO gap usually decreases because of this increase of energy of ground state of homoannular diene. Thus, the transition energy, you see the homo-LUMO energy gap is lowered, resulting in the shift of absorption position to a longer wavelength. right? Another type of conjugated cyclic diene is heteroannular diene. In heteroannular dienes, conjugated double bonds are not present in the same ring as in homoannular diene, and these have S-transoid configuration. You can see these three examples. The double bonds are present in two different rings, and these double bonds are in S-transoid conformation. You can see S-transoid conformation. That means the double bonds are present in opposite sides, to opposite sides of these two carbon single bond. You can see in these three molecules where the double bonds are in transoid configuration. These are transoid configurations, heteroannular dienes, right? Then see what is exocyclic conjugated double bonds. You know, the carbon-carbon double bonds projecting outside a ring are called exocyclic double bonds. That is, carbon-carbon double bond projecting outside a ring are called exocyclic double bond. For example, you can see in this molecule, it is the exocyclic double bond. This double bond, you can see it is projecting outside this ring, and so it is exocyclic with respect to this ring. Okay, but this bond, it is a double bond, but it is inside but not projecting outside, and hence it is otherwise called endocyclic. But it is important, it is exocyclic with respect to this ring because this double bond is projecting outside the ring. In the second example, you can see this bond which is projecting outside with respect to the ring A. This double bond is projecting outside with respect to this A, and hence it is an exocyclic ring with respect to this, exocyclic double bond with respect to this ring A. And so here is one exocyclic double bond. Okay, in the case of this molecule, see this double bond inside the ring B is exocyclic with respect to the ring A. It is exocyclic with respect to ring A. And similarly, this double bond, see this double bond, even though it is endocyclic with respect to A, it is exocyclic with respect to B because this double bond is projecting outside the ring B. Okay, and so this molecule containing two exocyclic double bonds. Consider this case, you can see this double bond which is endocyclic with respect to B, but it is exocyclic with respect to the ring A, and also it is exocyclic with respect to the ring C. Even though it is common to both the ring, but it is considered as two exocyclic double bond. That is one with respect to A and one with respect to C. Okay, and so this molecule containing two exocyclic double bond, right? Then we have to know what are the types of alkyl substituent and ring residue we have to consider while we are going to calculate the lambda max of organic molecules. You know, only the alkyl substituents and ring residues attached to the carbon atoms constituting the conjugated system of the compound are taken into account. Only the alkyl substituent and ring residues attached to the carbon atoms constituting the conjugated system of the compound are taken into account. The ring substituent or alkyl substituent which are directly connected to the conjugated system are taken into account while we are going to calculate the lambda max value. Okay, for example, in these two molecules, see this alkyl group, ethyl group, it is connected directly to the conjugated system, and also this methyl group also connected directly to the conjugated system, and hence these two are two alkyl substituent. In the case of this molecule, you can see this ring system which is connected directly to the conjugated system, and the ring residue that is connected to this conjugated system is these two ring residues. See this that is indicated by these dotted lines. There are two ring residues present in this molecule. Okay, see these two molecules where these two in this molecule, these two are alkyl substituents because these two groups are directly attached to the conjugated system, and hence these two groups are considered as two alkyl substituents. In this molecule, it is this ring that is connected to the conjugated system, and these two residues, alkyl residues or ring residues, we can say ring residues, these two residues are connected to this conjugated system directly, and hence we can say this molecule containing two ring residues, right? See, from these examples you will see how to determine the ring residues and alkyl substituent in a molecule. For example, in the first case, first of all we have to determine which is our system, that is homoannular diene system or heteroannular diene system. In this case it is heteroannular diene system. See, it is marked in red ink, and you can see there are three dotted lines which is marked for ring residues, and these ring residues are directly attached to our system, the conjugated diene system. So this molecule has three ring residues. Then consider this molecule. You can see our system is a homoannular diene because these two double bonds are inside one of the ring, and it is conjugated. So it is conjugated homoannular diene system. See the ring residues and alkyl residues directly connected to the conjugated system. It is denoted by this dotted lines. You can see there are three ring residues. One is this, another ring residue, and there is an alkyl substituent directly attached to this conjugated system, and hence this molecule has three ring residues and one alkyl substituent. Similarly, this molecule will have our system. It is actually a conjugated diene system in which you can see there are three double bonds. Two double bonds are inside one of the ring, and one double bond is in another ring. But all these double bonds are conjugated. Okay. But see, in this third case, you can see both the homoannular diene system and the heteroannular diene systems are present. We are taking homoannular diene system as our basic system because homoannular diene system absorbs more wavelength, or the lambda max of homoannular diene system, which exists as a cissoid system, absorbs more wavelength, or lambda max is greater than the lambda max for transoid system or transoid system, that is in heteroannular diene, which is a transoid system. It absorbs lesser wavelength compared to cissoid system in homoannular diene. So we taking into consideration, or we are taking homoannular diene as our basic system if a molecule contains both the system. Okay. Thus, in this molecule, our system is homoannular diene system, and you can see this homoannular diene system is connected with a conjugation. That is, another double bond is present here, so that there is it is the conjugated system. And when this conjugated system is taken into consideration, we will have this much ring residues and alkyl substituent present in this system. For example, there are two alkyl substituents present in this system, which is denoted by these dotted lines. You can see this dotted line indicates two alkyl groups attached to this system, and also there are three ring residues present, which is denoted by these dotted lines. Three ring residues within the system, or these ring residues are connected to our system, and hence there are three ring residues and two alkyl groups present in this molecule. Okay. It is how we can determine what are the or which are the ring residues or alkyl groups present in our system. That has to be taken into account in calculating the lambda max of organic molecule. Okay. Now let us consider Woodward Fieser rule for calculating lambda max in conjugated diene first. It is the empirical rule for calculating lambda max. See, base value for acyclic or heteroangular diene, that is 240 nanometer. That is for heteroangular diene and acyclic diene. The base value is 240 nanometer. See, it is 240 nanometer. For homoannular diene, the base value is taken as 253 nanometer. 253 nanometer. Then we have to give increments for alkyl substituent or ring residues, exocyclic conjugated double bond and double bond extending conjugation. And also certain substituents may be present in the system, and hence these substituents contribute some increments that also have to be considered. Okay, see the increments for each of the component. Alkyl substituent or ring residue, we have to add 5 nanometer as the increment. 5 nanometer. For exocyclic conjugated double bond, we have to contribute 5, or we have to add an increment of 5 nanometer in lambda max. For double bond extending conjugation, that means if a double bond is added as conjugation, for one double bond extending conjugation, it is 30 nanometer. Okay. Then if substituent such as alkoxy group is present, we have to add 6 nanometer as increment. For chlorine or bromine, it is 6 nanometer. Acyloxy, 0 nanometer. Alkyl thio group, SR group, alkyl thio group, 30 nanometer is to be added as increment. Dialkyl amino group, 60 nanometer is to be added as increment. See, if the same double bond is exocyclic to 2 rings simultaneously, that we had discussed earlier in an example, that is 10 nanometer. Then solvent correction 0 nanometer. Thereby the total calculated lambda max will be the total of all this amount. That is the lambda max calculated. Okay, it is the way by which we can calculate lambda max according to Woodward Fieser rule, right? Remember, in compounds containing both homoannular and heteroannular diene systems are present, calculations will be done based on the longer wavelength, that is 253 nanometer, that is by taking homoannular diene as the basic component. That means if we have a molecule containing both the homoannular diene system and heteroannular diene system, we have to take the homoannular diene system as the basic component of the system by taking 253 nanometer as the base value. Okay. Now let us take some of the important examples for calculation of lambda max. For example, this system, that is 2,3-dimethyl 1,3-butadiene. This is an acyclic diene with 2 alkyl substituents. You can see it is our basic system. This an acyclic diene system which contains 2 alkyl substituents, 2 methyl substituents directly attached to our system. So that calculation is as base value is 240 nanometer. There are 2 alkyl substituents and hence 2 into 5, that gives 10 nanometer. So that the total calculated value will be 224 nanometer. 224 nanometer. That is the lambda max of this molecule is calculated as 224 nanometer because it contains 2 alkyl substituents which are attached to the basic system, acyclic system. which having lambda max of basic value lambda max of the basic lambda max value of 240 nanometer. Then 2 alkyl substituent gives an increment of 2 into 5 nanometer, that is 10 nanometer. That is why the total lambda max or calculated lambda max will be 224 nanometer. Okay, that is the calculated lambda max value for this molecule, right? Next example, see this molecule is called myrcene. Our basic diene system is marked in red. See this curve, red curve indicates our basic system. It is actually an acyclic conjugated diene system which has a base value of 240 nanometer. Then this green drawing indicates the alkyl substituent. It is the alkyl substituent which gives an increment of 5 nanometer for the basic value, and so the total or the calculated lambda max for this molecule will be 219 nanometer. 219 nanometer. It is an acyclic conjugated diene system which has a base value of 240 nanometer. Only one alkyl substituent which is marked in green curve. That is why a 5 nanometer increment is to be added. That is why the total calculated lambda max of this molecule will be 219 nanometer. Okay. See this example. It is a heteroannular diene. It is a heteroannular diene, and hence basic value is 240 nanometer. The base value of our system is 240 nanometer. Then you can see there are two green or there are two ring substituent which is marked in green drawings. So 2 into 5 contributes 10 nanometer, and you can see there is an exocyclic double bond, exocyclic conjugated double bond, exocyclic conjugated double bond, exocyclic conjugated double bond, that is projecting outside this ring, which contributes 5 nanometer, so that the total lambda max or calculated value becomes 299. 214 plus 10 plus 5, total 229 nanometer. The observed value or the experimental value is 230 nanometer. Usually the difference between experimental or observed value and the calculated value is usually plus or minus 5 nanometer. Okay. Then another example, see this molecule. It is a homoannular diene, homoannular conjugated diene, and it has a base value 253 nanometer. 253 nanometer because it is a homoannular diene. 253 nanometer is the base value of this system. See, our system is marked in red curve, and there are 3 ring residues directly attached to our system. One is this, and the other is this, another is this, which is marked in green drawings. So there are 3 ring residues, 3 into 5, total of 50 nanometer is the increment for these ring residues. Then you can see an exocyclic double bond here. This double bond is projected outside this ring, and it is marked in blue curve, and so 5 nanometer is to be added for one exocyclic double bond, so that the total becomes 273 nanometer, and so the calculated lambda max for this molecule is 273 nanometer. Okay. Then take this example. It is a heteroannular conjugate diene. It has a base value of 240 nanometer. See our conjugate system. Our system is marked in red curve, and there are 3 ring residues directly attached to our system. One is this, another, and another. And so 3 ring residues are present in our system or directly connected to our system. And hence 3 into 5, a 50 nanometer is to be added in the basic value. Then you can see with respect to this ring, an exocyclic conjugated double bond is present, which is marked in red, blue circle. This is projected outside this ring. With respect to this ring, it is an exocyclic conjugated double bond. So another 5 nanometer is to be added, so that our calculated value becomes 234 nanometer. So the calculated lambda max for this molecule is 234 nanometer. Okay. And finally, this consider this examples also. It is a homoannular diene. See, it is a homoannular diene. See, this example consists of homoannular diene system and a heteroannular diene system also. But according to our convention, we have to take the homoannular diene system as our base component, so that the base value of this molecule is 253 nanometer. 253 nanometer. It is our basic system. Base system is this system, which is marked in red. It is base system, homoannular diene. It is the ring which is containing 2 double bond inside the ring. So it is homoannular diene. It is our system, and it is having an extended conjugation. If we pass through this, it is a double bond which is an extended conjugation. And so this extended conjugation contribute, one double bond extending conjugation contribute 30 nanometer. See, there are 6 ring residues. It is a ring residue, it is another ring residue. All these marked in green drawings or a green curve. You can see it is a ring residue which is directly connected to our system. It is another ring residue which is directly connected to our system. It is another ring residue which is connected to our system. It is another ring residue. This green, which is indicated in this green curve, is another ring residue. It is another ring residue. It is also another ring residue. So that we'll have 6 ring residues. 1, 2, 3, 4, 5, and 6. 6 ring residue contribute altogether 30 nanometer in the lambda max value. Then you can see there are 2 exocyclic double bond, conjugated double bonds. See, for example, this double bond is exocyclic with respect to this ring. This double bond is exocyclic. It is projected outside this ring, and so it is an exocyclic double bond. Also, you can see here is an exocyclic double bond with respect to this ring, exocyclic double bond. See, another exocyclic double bond which is common to both this ring and this ring. Common to this ring and this ring. It is this double bond is exocyclic with respect to this ring and this ring. And so 2 into 5. It is marked in blue curve, blue circle. You can see this blue circle is for exocyclic double bond common to this ring and this ring. And so 2 into this will contribute, this double bond will contribute 2 into 5. 2 into 1, that is 1 double bond exocyclic to 2 rings simultaneously. That is why we have to add a 10 nanometer, another 10 nanometer. So that the total value of lambda max becomes 333 nanometer. See these examples. See the example again. You can see the calculated or the total lambda max value is 333 nanometer. Right? With this example, I conclude this session. In the next session, we will discuss the lambda max value, the calculation of lambda max value according to Woodward Fieser rule of enones, that is alpha, beta unsaturated ketones. Okay. Okay, thank you for listening. Thank you.